everyone, welcome into lecture number 2. This lecture is on separable equations. So let's start with some motivation. This is motivation that we actually talked about in the last lecture. Recall from lecture 1 that we can solve equations of the form. Alright, we solved an equation. So a first order differential equation, FODE, of the form. This was our free falling body problem, and the form of the equation, if you take out all the letters that we had from our derivation of that equation, it's something like dy dt equals a times y plus b. So here a and b are real numbers, right? And y is the unknown function that we're trying to solve for. Y is a function of t. So when we want to solve a differential equation, we have to try to solve for this unknown function y. All right, so I'm just going to go through quickly the method that we used in the last lecture, and then we will expand this. So this will be motivation for us to define what we mean by separable equations. So what we did in the last lecture was we factored out this constant a from everything, and we wrote this equation as dy by dt equals a times y plus b over a. Then we divided through both sides of the equation by this term, y plus b over a, right? I'll just write it like this. And at the same time, we multiplied both sides of the equation by dt. So it's going to cancel over here, right? Remember, we're thinking of dt as a differential, so you're allowed to multiply, you're allowed to break up the derivative into its differentials. And now what we end up with is this equation where we have 1 over y plus b over a dy equals on this side just a dt. And of course this is now truly a differential equation. We have a differential on the left hand side with respect to y, a differential on the right hand side with respect to t. And what we did in the last lecture was we just integrated both sides. Now in this lecture I'm going to do something slightly different, just to get it in a form that we're going to generalize in a minute, okay? But I'm going to now subtract this differential from both sides. So I'm going to write all these differentials on one side. So, and I'll put the t variable first. So minus a dt plus 1 over y plus b over a dy equals 0. All right, and so at this point, what's on the left-hand side, this is called a total differential. So this whole term right here is what's referred to as a total differential. All right, and a total differential is something that can be integrated, like we said. So now we just integrate both sides and see what happens. Now I write the integral on both sides because we have to remember that we're going to get a constant from something, right? But on this side, we just integrate. So this minus is going to stay here. So this becomes minus a times t, right? Plus this one is now a natural log. So this is the natural log of y plus b over a, absolute value. And on this side, we get our constant c. All right, and so that's how we solve the differential equation. We have written it as a total differential equals 0. Integrate both sides. We get this term over here, which is now an implicit function. The y is wrapped up in here, equals a constant. Okay, now in some sense, I'm going to undo exactly what I did up here, because if possible at this point, so this right here is an implicit solution before I go to the next step. Implicit means that we have not explicitly solved for the y that we're looking for, right? Because remember, our job, try to find this function y as a function of t. Implicitly, we've done it, right? We've gotten rid of the derivatives. We now have an equation that relates y with t, right? And there's this unknown constant involved. But if possible, we would like to try to solve for y explicitly. To do that, like I said, I have to undo exactly what I did up here, but it's okay. So I'm going to add the at over, and then we can solve from here. So we did this in the last lecture. So now I get this log equals a times t plus c. All right, when I exponentiate, we have this trick where the absolute value here is going to, so I'm going to just write it this way, because again, we did this in the last lecture, but when you exponentiate, the sum becomes a product, and then this c, because of the absolute values, can just become any constant c. So maybe we'll call this one c1, and this is c2. it's a different constant, right? So in this case, C2 is equal to plus or minus e to the c1, and the e to the c1 comes from the exponential, and the plus or minus comes from dropping the absolute value bars here. But it's unknown. It's an unknown. They're both unknown, so we just replace it with a nicer, simpler version, right? And as I do that, I'm going to actually erase the c2, the 2. Okay, I'm just going to leave this as c. And finally, so now we're almost done, right? So the last step is just to solve for y explicitly. So y is then going to be equal to unknown constant, e to the at minus b over a. All right. B and a are known constants. So we're assuming that we were given the numbers a and b, right? They're real numbers. They're known constants. C is an unknown constant. So this is actually a family of solutions to our differential equation. Okay. So, but that's it. That's the solution. Now, we want to generalize that to other kinds of equations that are, in some sense more complicated. So we'll call this item 2, generalization. All right, so the basic idea of what we did up here was we were able to separate our differential equation, which came as kind of a derivative. I like to call this a derivative equation, but I don't think anyone else in the world does that. But we were able to separate our differential equation into these two parts where one part of the differential had only t's, right, and the other part had only y's. Remember, the a and b are constants. So that's the whole idea of separation, right, separable. We're going to be able to separate our differential equations into total differentials, which separate the variables, x and y in this case. So I'm going to write a definition here. I'll even write definition for us so that we know that that's what I'm doing. But a first order differential equation, I'm going to abbreviate a lot of stuff here, but a first order differential equation is said to be separable. So separable, this is what we're defining, if and only if it can be written. Notice I'm not saying it is given to you this way, right? But it can be written in the form of the following. So first of all, remember, our first order differential equation is given to us as a derivative, dy by dx equals f of xy. All right, so I'm going to highlight this. This is our given first order differential equation. All right, that's this. All right, now the can be written in the form, I'll highlight in yellow. So right now this is just a general first order differential equation. If I want this to be separable, then the definition says, the definition that I'm writing here, right, is that we can write this in the form, the following: some function m of x times dx plus some other function n of y dy equals 0. And so there's where we get our total differential, right? We can see exactly, we've now separated this out. So we've separated this out. And so that's our definition of a separable differential equation. We can rewrite it from this given form. We can find a way to write it in this form, right? And maybe it's given in this form, but this was our general definition of a first order differential equation from the last lecture. All right. Now, how do you solve these? Well, you do exactly what we just did, which is you integrate through, you get your constant over here, and then if possible, you try to solve explicitly for your function y. You're going to get an implicit solution just by integrating this. Okay? So there's our definition, and here's our method of solution. There's going to be a whole lot of integration in this course. All right. I remember when I first took differential equations, my professor told me that by the end of the course I would be a master integrator. So that's one of our goals. We know how to integrate now. It's a prerequisite that we know how to integrate, but you're going to really be able to master that skill by the end of this course. So the method of the solution here is just integrate. All right, and then if possible, so then after you've done that, if possible, and if appropriate, so I'll write both here, if possible and appropriate, then we're going to solve explicitly for y. Okay, let's do an example together here. I'm going to call this one I'm not going to number this one, but this is an example. So let's say we want to solve the following equation. Y prime plus y squared sine of x equals 0. All right, so this is our job to solve this. Right now, this is not currently written in the proper form, right? So I'm going to put a star up here. This is our goal, to get our equation into this starred form. It's not currently in that form, and it's not clear yet if it's even possible. So this may or may not be a separable equation. Since it's our first example, we can guess that it will be, but that guessing's not good enough, right? We have to actually check it. So the independent variable in this equation is x, not t. It was t in my previous example, but it's x here. So that means our derivative is actually dy by dx. And this equation, or this part of the equation, can stay the same. All right. Now to separate through, what do I have to do? So to be able to separate, what I'm going to have to do is divide through by the y term here. So that's going to go over here, right? And then also multiply everything through by dx. And so multiplying the whole equation by dx, dividing the entire equation by y squared, this is going to give me the new form of the same differential equation, right? 1 over y squared dy plus sine of x dx equals 0. And now this is in the separable form, right? So we have checked off that equation star is satisfied. Remember, it's right there, right? So it's it's in the opposite order, but that's okay. The order of these two, these are added together, so it doesn't matter. But we've got sine of x dx, so our function m is sine of x, and then n of y dy, so our function n is 1 over y squared, right? At this point, we just have to integrate. So I'm just going to throw an integral in front of the whole thing here, and let's see what happens. Antiderivative of 1 over y squared is negative 1 over y, right? So negative 1 over y, plus the antiderivative of sine of x is actually negative cosine of x, right? So minus cosine of x. And then over here, this equals c. So this equals c. All right, at this point, what do we have to do? Well, we can multiply through here by a minus sign, and just kind of like the trick that we did before, it won't affect our c here. So we can actually rewrite this as 1 over y plus cosine of x equals unknown constant c. And then remember, so technically this is our implicit solution, right? For any value of c, we'll have an implicit solution for y. But part of the second half of our method of solution up here was, if possible and appropriate, solve explicitly for y. This one we can solve for y, so that's what we're going to do next, right? You just have to subtract cosine x from both sides and then take the reciprocal function, and what you end up with is the following. So we will get that our function y, which is a function of x, right? So I'll even write it explicitly. Y of x is going to be equal to the reciprocal here of 1 over unknown constant minus cosine of x. And so there we go. There's our explicit solution to this differential equation. All right. So at this point, I would like you guys to try one. So let me write it down. There's the method, though. That's the method that we're going to use. So this is number 3, another example. All right, this equation, I want you guys to solve for r as a function of theta. All right, from this differential equation. It's a very simple differential equation, but you have to start somewhere. So dr d theta, in this case, is equal to r squared over theta. Okay, so take a minute to write this one out yourself, and then we'll solve it together. All right, so now that you've had a chance to work on that one on your own, let's do it together. So what we want to do here is actually separate our variables, right? So we can kind of do like a swap of these two, and this becomes 1 over r squared, again, that's very similar to what we just had, dr equals 1 over theta, d theta. And actually, this is okay. So this is not exactly in the form of our equation star, but we can just work from here. We don't have to actually get it exactly in this form every single time, as long as we can see that the variables are separated and we have an equality of differentials. And this is how we solve the free-falling body problem in our last lecture. At this point, we just integrate. Now, the one thing you have to remember here, the reason that this is maybe nicer, is that the 0 over here reminds us that we have an unknown constant, right? I mean, hopefully we would never forget that unknown constant anyway, right? Because we're going to become master integrators. But it's like visually it reminds us when we see this equation. In this equation, we just have to remember to add it at some point, right? So again, when we integrate this entire equation, this time we can just throw a couple integral symbols on each side of the equation. The left-hand side is minus 1 over r, which is similar to what we did before. And this one, right, is going to be natural log of the absolute value of theta. Here, I'm going to put the plus c over here, because remember, our job is to solve for r as a function of theta. Very similar to what we did on the previous one. Now we just have to solve for r, right? So I'm going to do, again, something crazy. I'm doing this because you're going to see this as you work through, you know, during the learning process. You're going to see other people do this. So I'm just going to do it now. But if I want to change, we want a positive r, right? So if I want to change the sign and multiply through by a minus, this will become positive 1 over r. This is negative log of absolute value of theta. This I'm going to leave as plus c. Well, why? Because it's already unknown, right? It's unknown. So if I change the sign on it, it's still unknown. All right? So changing the sign, this becomes 1 over r equals negative log of theta plus c still. And then the reciprocal gives us our answer, right? R of theta is going to be 1 over, and I'll write this as c minus natural log theta. Okay, so this is called the general solution, because this is actually a family of solutions. So this is the set of all possible solutions of this differential equation, general solution, and the all possible comes from this unknown value c. All right, so this raises a question. That's the end of what you guys did in the pause and pencil, hopefully. But this raises another question, right? So here's a question. Can I determine C? So is it possible? So can we determine the value of this unknown constant C? And the answer is yes, but, well, maybe, right? In certain circumstances, the answer is yes. And the answer is yes when we are given extra information, right? So if we are given more information, in this case, I'm going to call this an initial condition. An initial condition. It also could be referred to as an initial value sometimes. But if we're given an initial condition, then the answer is yes. All right, so what do I mean by an initial condition? Well, remember we plotted some slope fields, and we'll do one in one of the examples later on in this lecture. But we plotted slope fields in the last lecture, and we talked about the different behaviors of the solutions depending on where we started drawing our solution curves, right? Based on the slope field. Well, the initial condition just tells you where to start drawing your solution in some sense. All right, and so for this one, this is now extra information. So I'm now changing the problem. I'm adding information, right? So I'm going to say, all right, let's suppose that we know for some reason, maybe we took a measurement, we did an experiment, maybe something like that, right? Then somehow we know that r of 1 equals 2. So in other words, when theta equals 1, r is equal to 2. All right, we know this somehow. Again, it could be experimental, it could just be an assumption, it could just be a guess, whatever. But we know this information. Then what we can do is plug into our solution to solve for C, because now we have fixed data for r and theta, right? So we can plug this in to the general solution. What we're going to obtain is a particular solution to the problem with this initial data, right? This initial data. And so remember our r, this is our solution, right? R of theta equals 1 over c minus log of theta. Just check, make sure I copied it right. And so when we plug in, this is going to say what? R of theta is 2 by the initial condition equals 1 over c minus natural log of 1. All right, natural log of 1 is 0, right? So this is 1 over c, and so this implies then that our c is equal to 1/2, right? Just reciprocal. And so in this case, we can write down a specific solution or a particular solution. The official term is particular, not specific, but it is specific in the English language. But it's a particular solution to this initial value problem. So that's what we're going to call these, all right? Initial value problem means you have a differential equation together with this initial value, initial data, all right? This is then the function r equals 1 over, our c is 1/2, right? 1/2 minus log of theta. And then if we just multiply through everything by 2, then this could become 2 over 1 minus 2 log of theta. That's just to get the fraction out of the fraction, right? And at this point, if we want, you can apply a log rule to make this look really, really beautiful. And so our final answer here is going to be r of theta, the solution of this differential equation, with this initial condition that I wrote up here, is going to end up being 2 over 1 minus log of theta squared. Okay? And so that's how you solve what's called an initial value problem. All right, let's do another one then, another initial value problem. I'm going to abbreviate initial value problem as IVP moving forward. So here's one. Solve the initial value problem, or IVP, that is given by the following. So this time we need, if we're going to have an initial value problem, we first need a differential equation. So the differential equation for this example is going to be given as a rational function here. So dy by dx, that's our derivative. So x is our independent variable, equals 3x squared on the right-hand side, plus 4x plus 2. All right, all divided by, so everything's on the right-hand side here, right? But 2 times y minus 1. And then the initial condition. So right now, this is not an initial value problem yet. This is just a first-order differential equation, or a FODE. And the initial condition that we want to talk about for this one is y of 0 equals -1. This is additional information. Okay, that's additional information. You can't, again, this, in practice, this will come from a lab or from an experiment or something. It's your initial measurement of whatever you're studying. Okay, so I'd like you guys to take a moment to try to solve this one yourself, and then we'll come back and do it together in a minute. Okay, so now that you guys have had a chance to do this one on your own, let's do it together. This one is definitely separable. So again, the idea is that this term can get multiplied to this side, right? And then we can just multiply this differential over to this side. And what we will end up with is, then is a differential equation that looks like this. So 2 times y minus 1 dy equals this entire term, 3x squared plus 4x plus 2 dx. We can just integrate, so this part's not too bad, right? And what we end up with then is, just multiply this through, I guess. Yeah, so this one's going to end up being 2, this one's going to be what? 1y squared, right? So, sorry. This one's going to be y squared minus 2y on this side. And on this side, it's going to be x cubed plus 2x squared plus 2x. And here's where our plus c comes in. All right. And so at this point, we have a implicit solution, right? it would be very nice if we could solve explicitly for y, especially since we have this initial value. So at this point right now, we can actually plug in our initial value, but we're still going to have to solve this equation explicitly for y at some point, right? So I'm going to write down we have two things to do. So 2 steps left. Number 1 is figure out what c should be, and number 2 is solve explicitly for y. And they can be done in either order, but I'm going to do it in the order that we wrote, because what we know from this initial condition, is that when x is equal to 1, when x is equal to 0, y is equal to -1. And so we can just plug this in, right? So on this side, we'll plug in our -1 squared minus 2 times -1. And on this side, we'll just plug in all of our zeros, right? 0, 0, 0. This is just c. And so here we have 1 plus 2 equals c, so obviously then c is equal to 3. And now we can write down go back to this equation, right? And just plug in c to this equation. And we can write this down as y squared minus 2y equals, I'm actually going to leave a little room there. All right, but this equals x cubed plus 2x squared plus 2x plus 3. Right? We've solved for c, but we need to explicitly solve for y. So to solve for y, we have to complete the square, right? So we can complete the square by just having this, squaring it, so I hit to add 1 to both sides. So that's going to make that a 4 now. So we solve for our c first, and then determine our constant's actually going to end up being a 4, right? Over here we have y minus 1 quantity squared, factors, right? On this side, we have all of this, so x cubed plus 2x squared plus 2x plus 4. And then we have to square root, add the 1. We end up with this, y equals 1 plus or minus, right? Square root of all this stuff. So this is x cubed plus 2x squared plus 2x plus 4. And the question now becomes, which sign should it be, right? Should it be the plus or should it be the minus? Because we need a function. A function can't have two outputs. So should it be the plus or should it be the minus? And the answer to that comes from our initial condition again, right? Our initial condition says that when x is 0, y should be -1. Well, look at this. When x is 0, right, this becomes 1 plus or minus 2, right? So y of 0 is equal to 1 plus or minus 2. So in other words, it's either 3 or it's -1. Well, we don't want 3, right? So at this point, we know that we can't keep the plus. We just keep the minus sign, right? And if we keep it for the initial condition, that's what we get for the entire function. All right, so the initial condition tells us to keep the minus sign. All right, so we'll keep the minus sign on that. And what we end up with then is that our particular solution is now y equals 1 minus this square root, right, of x cubed plus 2x squared plus 2x plus 4. There's our explicit solution. All right, so let's graph this thing. Let's try to see how this looks. So what do you think the domain? We need to know the domain, right? So one thing we could do is just try to figure out what the domain is just by investigating this as a function, as a purely calculus function, and try to find out what any restrictions on x would be. All right. Another way, though, is to look at the slope field. So the question now is, what is the domain? And we're going to use the slope field to help us. Okay, so I'm going to switch over to my Sage Math, and then we'll plot the slope field. Okay, I've opened Sage Math. I have a notebook open here, and we'd like to plot the slope field for our differential equation. So remember, the first thing that we have to do is define the variables. X is already defined. It doesn't hurt to redefine it, but y is not defined, so we have to define y for sure. And then we need to define the right-hand side of our differential equation. So as far as the slope field is concerned, we want to keep this in the given form. So our differential equation was dy dx equals 3x squared plus 4x plus 2, all right, divided by 2 times y minus 1. All right, and now we want to plot the slope field for this, right? So I'm going to name this and then we'll print it in a minute, but this is going to be plot slope field of f. We did this last time. Let's do from the initial condition is y of 0 equals -1. So we're not really sure exactly what the x's need to be, but let's go from -4 to 4 in both directions and see if that's enough. All right. We can always change this later, right? So I'm going to give this a title. And it is y prime equals this, right? So again, it's 3x squared plus 4x plus 2, and then 2 times y minus 1. All right, so that runs it. We can see it by doing this. So that SF just saved it. And here's our slope field. So notice that the slopes are very erratic. This is a little more complicated than the ones that we looked at last time. But what we need to do now is consider our initial condition. So our initial condition was y of 0 equals 1. So when x is 0, y is 1, right? Negative. It was -1, right? So when x is 0, y is -1, so it's down here. But let's actually plot that on there. So I'm going to call this IP for initial point, and we will plot this in there. So this is 0, -1. Let's make it big enough to see, and make it red. So there we go. So there's our initial point. So when x is 0, y is -1. Now the question, so our solution curve has to pass through that, right? And we can kind of see the behavior of how it's going to behave now, right? So how is this thing going to behave? Let's plot our solution itself. Remember, our solution was the following. So notice that the problem here is going to be that, let me go back to the notes. We want to try to find the domain, right? So this is our solution. The problem is going to be finding the domain that we want to plot this thing on. So based on the slope field, what could possibly go wrong? That's what we're trying to figure out by looking at the slope field. As you try to sketch the curve that passes through this point, you see that it's going to kind of dip down here, and at least in the window that we've plotted the slope field, everything's going to be okay over here, right? There's going to be a nice curve. It's going to be smooth, meaning that there's no breaks, no jumps, no corners even, right? As we go this way, it's pretty good. It kind of is going to level off, and then it's going to turn, and then look at around here, somewhere around here, looks like it's going to become vertical. Well, the problem with a vertical curve is that it's not, if a curve actually becomes truly vertical and it stays that way, right, then it's not a function, right? Especially because after it becomes vertical, if we just imagine what the slope field's doing, after it becomes vertical, it looks like it's going to curl back around over itself, and then it's going to fail the vertical line test, right? So our solution is a function, but the curve that looks like it should pass through this point is not a function, right? And so our domain restriction is going to be the point where this thing does its turning, where it turns around. That's going to be the end of the domain on the left-hand side, the boundary of the domain on the left-hand side of our function. So we need to figure out where this is going to happen. Well, what could possibly make that go wrong, right? Our derivative, if the curve becomes vertical, then the derivative is undefined, right? And the derivative will be undefined if the bottom is equal to 0. So if y is equal to 1, right? If y is equal to 1, the denominator will become 0, the slope will become undefined. So let me write this down. But here's our obstruction. The obstruction, right, is that if y prime equals 0, then our domain is going to we're going to have a problem with our domain, right? Not 0, not y. It's if y prime is undefined. if y prime is undefined, then our curve is the domain is going to have to stop, right? We're going to have an obstruction. And from our differential equation, that's going to happen if y equals 1. So the domain, the derivative will become undefined if y equals 1. So this happens when y equals 1. And based on this, right, this will become, this will be 1. So 1 equals 1 minus the square root x cubed plus 2x squared plus 2x plus 4. Then it's going to happen when this part equals 0, right? So this part equals 0. So x cubed plus 2x squared plus 2x plus 4. This can be factored by grouping if we need to, but the whole idea is that this will be equal when this is 0. So if we do this by grouping, what are we going to get? X squared times x plus 2 times x plus 2 equals 0. So x squared plus 2 times x plus 2. All right, and so notice that we have x from this one. X is going to be equal to, well, this one is going to be undefined. This one's not going to have any solutions, right? X squared plus 2 can never be 0. But this one right here, this is 0 if x is equal to negative 2. So there's our obstruction. So from an analytical point of view, there's our obstruction. And so our domain should be, the domain has to include the initial point, so it has to include 0. And the obstruction is that it can't equal negative 2, right? So now analytically, our domain should be, of our solution, should be from negative 2 to infinity. All right, and let's plot our curve and see what it looks like back in Sage. So again, this is our domain. We use the slope field to help us get this, but ultimately we just did a little algebra here. But let's plot it. So I'm going to call this y1 equals 1 minus square root of, so our function, if we just go back, was x cubed plus 2x squared plus 2x plus 4. So x cubed plus 2x squared plus 2x plus 4. And then I'm going to also do y2 here just for the sake of comparison. Let's see what the plus does. The plus is the part that we threw away, right? The plus portion. And then, all right, so I'm going to plot both of these. And our domain is going to go from negative 2 to 4. Let's call this one, let's make this one blue. So that's our actual solution. And then C2, we're going to plot our curve y2 on the same domain. So x goes from negative 2 to 4. I'll make that a lighter shade of blue. All right, and so now I want to look at everything together. And so at this point, we just want to look at all of these together. So our slope field, our initial point, our first curve, and our second curve. And oh, the window is very crazy. But we can kind of see what's going on. We can fix this. So we just have to say our y min is negative 4 and y max is 4 for both of these. There we go. Beautiful. So when we look at this, we see here's our initial point, right? The dark blue, that's the curve that we found by solving. Right? This is our true solution, right? So this is our function that we found. And then what happens? Well, at this point where the color changes from dark blue to light blue, the derivative has become undefined because the curve is now got a vertical tangent line, and then it curves back over, right, above itself. So it's not a function. It fails to be a function. And the light blue, the cyan colored curve, that's the half of the square root that we threw away. So that's the plus square root portion that we threw away. All right. So this is an example, and we've kind of stumbled through it here a little bit with at least with the plotting and stuff. It's taken a little bit of a long time, but we've dug into it in detail, and I hope you understand now that the initial condition picks out the curve, right? But as far as the function is concerned, the function and the curve are not necessarily the same, right? Because the function is only going to give us the dark blue, the function solution, the functional solution. The equation that we write down gives us the dark blue portion of the solution curve, right? This upper portion of what is kind of a continuation of the curve is not given by that function. That's the plus square root portion of the function. Okay, so that is, again, an example of an initial value problem and kind of an outline of some of the subtleties of what can happen when you're solving these. We have one more thing that I'd like to talk about in this lecture, and that is homogeneous equations. We talked about homogeneous equations in our classification section of lecture 1, and this is a completely different meaning of the word homogeneous. All right, so it turns out homogeneous is one of those words that shows up all the time in math, and it means, many, many different things. Maybe even up to like a dozen different things in different areas of math. Homogeneous means different things. So I'm going to define now a different kind of homogeneous than what we defined before. And here's what it is. So a differential equation, a first order differential equation. So I'm going to write it like this. Y prime equals f of xy. So we'll have x's and y's as x is our independent variable. So that's a first order differential equation and kind of what we've deemed to be the standard form. This is called homogeneous, or it's said to be homogeneous. Again, in this sense of the word, homogeneous if and only if with a double F means if and only if, it can be written in the form y prime equals some other function g of y over x. So now this g is a function of one variable, but the variable it takes in is a ratio of y over x. This is the key. This is what makes it homogeneous in this sense. That the right-hand side of the equation can be written in terms of this y over x, and what we will do then is make a change of variable. So we're going to investigate what this whole idea of homogeneous equations by solving an example problem. So a motivational example, we'll call it. This is a motivational example, and it's the following. So dy by dx is equal to 4y, in this case, minus 3x, divided by 2x minus y. All right, this is not separable. Notice that it is not separable. This equation is not separable. You can't separate the x's and the y's. But what we can do is if we divide through by x, so really what I want to do is I kind of want to multiply top and bottom by 1 over x here. All right, then number one, I'm making a restriction. So the second I do this, x can no longer be 0, right? So x equals 0 is not allowed. But as long as I make that restriction, actually, let's fix it to be x is positive. All right, so if we make this restriction where x is actually positive, you can switch it to negative later if you want. But if it's positive, then you can do this. And then what you end up with is this equation where dy by dx is equal to 4 times y over x minus 3, those x's cancel, over 2, they cancel, minus y over x. And so there we go. There's our g. Notice now we've got exactly what I've claimed we're looking for, right? We're looking for y over x's and nothing else. So this now is a function of just y over x on the right-hand side. All right, so the method of solution then, so to solve, what we're going to do is make a substitution. So make a substitution. We're going to let v equal this y over x. So these are just going to become v's. All right? But the consequence of doing that is that now we've wrapped up our dependent variable, our unknown function y, in terms of v. So another way to write this would be that y is equal to x times v, right? And this v depends on x as well. So the v itself is a function of x. Okay? It's an unknown function of x. But what we're going to do is solve for this unknown function v now. So that means we need to consider, right, what's going to happen to this derivative here. So we have to take the derivative with respect to x of this thing. And that, you can just see, right, is going to require us to use a product rule right here. All right, so just from this equation, we see then that y prime dy dx, right, is equal to product rule. It's going to be v, derivative of this times this, plus x times dv by dx. So all of this is going to go in, all of this is going to go in for this right here. Okay? So our equation now becomes, we end up with this. We end up with v plus x times dv by dx equals the right-hand side with v plugged in for that, right? So this now becomes 4v minus 3 over 2 minus v. All right? I claim that this one is separable. And if it's separable, then we can solve it. At least we can at least get an implicit solution, right? But we can solve it. So take a moment, solve this one on your own, and then we'll check back in and finish it off together. All right, so now that you've had a chance to work on this on your own, let's work on it together. The first thing that we need to do is, if we're going to separate it, right, the x dx, that part's fine. We need to get all the v's on this side, right? So we have to subtract this v to both sides. So step one is to subtract v. So we're going to end up with 4v minus 3 over 2 minus v minus v. And then, of course, we need to find common denominator to add this up into a single fraction. All right. Then we're going to have x times dv by dx. Just going to add this up first, and then we'll combine. But what are we going to have? So on numerator, 4v minus 3. Then it's going to be minus 2v plus v squared. This is all over 2 minus v. And then to separate this, we need to make sure the differentials are on top, right? The dx is in the numerator. So all this has to come over here, and we need the reciprocal of this on this side. So it's going to end up being, and I'm going to rewrite this a little bit, minus v plus 2 divided by, this is going to end up being v squared plus 2v and then minus 3 dv equals, on this side it's 1 over x dx. So we're going to get a log over here. And by the way this works, you're always going to end up with the same thing on the right-hand side for the x's. The v terms are going to all be different, right, depending on the differential equation. But if it is homogeneous, then you're always going to be able to separate this term like this. So x dv dx equals something with only v's. And then when you separate it, you end up with these two, right? All right. Well, how are we going to solve this? This one, you can investigate. You can try to do a u sub. If you do a u sub on the bottom, you need to have a 2v plus 2, the derivative, right? And we don't have that. We have negative v plus 2. So instead of doing that, we can do partial fractions on this one. So this one's going to require partial fraction decomposition. Meanwhile, this one is just natural log, right? So this is ln of x, and we'll put our plus c on this side. So this one requires a little more work. The bottom of this factors, right? So this one can be written minus v plus 2 over, this will factor to become what? V plus 3 times v minus 1 adds to 2, multiplies to negative 3. And so partial fractions say that this becomes a over v plus 3 plus b over v minus 1. And before doing anything else, we can just integrate this, right? So we're going to have to solve for the a and the b. I'll do that in a second, but I'd like to get this integrated first. So I don't know why. Let's just solve for a and b first. It's probably better if we solve for these first, right? And so remember, the way that this works is you multiply through by the common denominator. Negative v plus 2 equals a times v minus 1 plus b times v plus 3. And now for this one, you can just pick convenient values of v. So if v is equal to 1, then this is gone. This side becomes 1, 2 minus 1. This side becomes 4b. And so b is equal to 1/4. If v is equal to negative 3, that's the other convenient value, because it's going to get rid of this term, then this side is now 5, negative 3, right, times negative 3, so 3 plus 2 is 5. And on this side, it's negative 4a. And so a is equal to negative 5/4. All right, and so now our equation up here, or our function, our integrand, the thing that we need to integrate, is going to become negative 5/4 times 1 over v plus 3 plus 1/4 times 1 over v minus 1. All right, and remember, this is all going right here. So now we're going to integrate all of this with respect to v, and what we end up with is the following. I'm going to have to be, this is kind of a mess, right? So I'm not really writing this in a good organized fashion, but negative 5/4 natural log v plus 3 plus 1/4 natural log v minus 1. All right, and we can then do a couple of things. So this negative 5 can go in, we can combine these into a single log, and then yeah, so everything can get combined here. So this is all going to end up being the natural log of the 4th root after some careful log expansions, right, of the absolute value of v minus 1 over v plus 3 to the 5th power. So I'm not sure if that makes it better or worse, but that's what that becomes, all right, just by using your log rules to write this as a single log. And now we can finish, right? We're not going to be able to solve for v, but we can finish by setting this left-hand side equal to this right-hand side to get our implicit solution, at least. Okay, that'll give us our implicit solution. And so that can be written as follows. So our solution is going to be this. If you want it, you could have just left it as this, honestly. But if you want it as a single log, then it's going to be the natural log of the 4th root of the absolute value of this ratio. So v minus 1 over v plus 3 to the 5th power equals, on this side, natural log absolute value x plus c. So there's our implicit solution. Okay, so that, it got a little crazy at the end there, just with some crazy logs. But the main idea of this one is right here. So if you notice that your equation is homogeneous, you make this substitution, and then you solve for v. Yeah, we're not done. So we got I did this, right? This is my fault. But I just got so carried away in the solving of that differential equation, of the integrating, that I have forgotten the most important thing, right? Which is that we made this substitution for v equals y over x. We need to get this back in terms of y and x, right? So our solution is supposed to be in terms of y and x. So this is not the end. So the last thing is to sub back in, right? Our v equals y over x. And then we'll have our implicit solution in terms of y and x. All right, so what we end up with then is the following. We're going to get our natural log of the 4th root of absolute value, right? This y over x goes here. So y over x minus 1 over y over x plus 3 all to the 5th power. Okay, and this equals natural log of x plus c. And at this point we can multiply through by x to the 5th power, but it's going to be a mess down here. So we're going to just leave it like this. But so The key here is that this box is not the answer, right? Because that's still got v in there. What we want is this box that has our implicit solution in terms of x and y. So that's our solution. All right. So we'll leave it there for this lecture, and I'll talk to you guys in the next one.